Okay, good afternoon, everybody. I'm Guilherme, and I'm one of the monitors on this year's AstroCamp, and I was a student of 2020 AstroCamp as well. And today I'm here to talk about rockets, how do they fly, and how to build one. This is based on the work of my rocket building society I've been working with, Endeavor Rockets. So before I go into rockets in itself, there's a question. Why are rockets important? Why talk about this? Why are they relevant for our life nowadays? So let's think about our scientific advancement and how that depends on space. Okay, for example, telecommunications. We wouldn't be talking through phones or using GPS if we didn't have satellites that allow for telecommunications. That all needs a rocket to send them. We've been doing that since the late 90s. There's also space exploration. We wouldn't have International Space Station. We wouldn't have gone to the moon if there wasn't a rocket to start with. And of course, there's loads of telescopes. There's Hubble, there's the James Webb Space Telescope that we are sending things to space very frequently, and this frequency is increasing. However, in the future, this frequency needs to increase even more. One of the examples is this project. This is a space-based solar power project. Basically, you will get a bunch of mirrors that will concentrate the light from the sun in the atmosphere, concentrate everything into a single point satellite that transforms that energy into a radiation that is transparent to the atmosphere and that can be used in the ground. This technology has the potential to be way more efficient than our current solar panels and to produce solar energy 24/7. Also, the fact that this satellite goes around the Earth would allow us to give energy for free because it will not be used to third world countries. How this has the potential to revolutionize the way we see technology and the way we deal with it in our day-to-day lives. Why am I talking about this? Because this is only one of the projects and it's still a model. But one of the places that is developing things similar to this is the Catapult in the UK. And they started studying, okay, how can we do this? How can we send these things to space? And so they went to SpaceX, one of the main companies that sends things to space. And they asked them a very simple question. Okay, how many launches will you need? And the answer was, well, if you want to do this properly, we need a launch every other day. You can see just how much we need to increase our frequency of launches if we want to meet these kind of goals. And this is just one example of one scientific project, and in this case, one energetic project that could help solve our dependency on fossil fuels that relies on us having good rocket technology that can be reusable and that exists in number enough to allow for this kind of things. So that's why it's important to study rockets. That's why rocketry is important. So what is rocketry? Rocketry is the science that studies rockets. Everything from the rockets you can build in your backyards to the rockets that you send to the moon, to Venus, to anything. What does it do? It not only studies how they fly, but the conditions they need to fly, the aerodynamics, the shape, how much mass you can put in there, how the electronics in the rocket should be used, how can we make our flights more efficient, what kind of fuels should we use. As you can imagine, there's a lot of things you need to study in rocketry. And as this very big diagram shows you, there's loads of small steps you need to consider to have a successful flight and to be able to put instruments in orbit. So our goal in the end, what it is, it's to get something like this. This is a SpaceX flight landing on itself. It's the result of many years of engineering and mainly involved loads of people doing this. Sorry, the sound went off, and here we go. These are the results of multiple trials of amateur rocket scientists. These are all the things that can go wrong in a flight, in a small simulation. And if this is what happens with the small rockets, can you imagine everything that can go wrong with real life space flights? This is actually the trial for space vector thrust vector control, the exact same technology that SpaceX uses, but in a small scale. Basically, I'll talk more about this, but you're trying to make sure your rocket goes up like this and doesn't wobble, and then goes down like this without wobbling. And that's actually more tricky than it seems. So what are we going to talk here is not about big rockets. Big rockets involve big teams and involve a lot of mathematical knowledge. What I want to talk here is the basic science behind every single rocket and the kind of science that you can scale up to build this kind of rocket. So what I'll be going to be talking about is about amateur rocketry and the basics of rocket building. So what I'll start by doing is by explaining a bit of the physics and yes, the chemistry of rocket flights. And then I'll go over the anatomy of a rocket, everything that you need to consider when you're building a rocket, the different parts, and how you should structure your reasoning when you're thinking about building a rocket. Then cool things you can do with it, because amateur rocketry is not only about building a rocket, it's about performing experiences and learning new stuff. So what kind of things can you take from these activities? And then 2 or 3 links and tips about where to start to build rockets, because the idea of this presentation is by the end of it, you have a quite good idea of how can you start building your own rockets and what should you do first and what you would like to learn. So let's start. First, the physics of a rocket. Don't get too much scared about this equation. This is basically to explain that a rocket is basic physics. Basically, it's a variable mass problem. What you're seeing here, it's a differential equation called the rocket equation that tells you what you have in a rocket is 2 different kinds of mass. One very big mass that you want to go up, and the mass that goes with the rocket, and that is going to be expelled down with the rocket. And as you know, conservation of momentum, if mass goes down very fast, the other mass will go up very fast. And basically, that's how you need to know about the physics of a rocket. Knowing the mass you're going to have in the top part and knowing how much velocity you need to expel your second mass to have enough thrust to leave the atmosphere is the basics of rocket science. That's how you need to know about your engine to be able to put a load in the atmosphere. Of course, this is simplified. It doesn't have hair drag or other conditions and doesn't account for the wobble of the rocket. But basically, if you think about how to start building a rocket and how it should start to work, that's the first thing you should consider. A very simple differential equation that tells you how much mass you need in terms of rocket fuel in order to get the mass up there. And of course, how much energy you need the rocket fuel to go with, because if you don't expel the mass with enough velocity, it will never go up. So now you know how much mass you need, how much velocity you need. How can you get that? How will your rocket actually expel that mass? That's where the fuel and the propellant come in. This is a bit more of chemistry than physics, but basically what you have is a oxidation reduction reaction. Basically, you're catching something on fire, and that explosion will propel your rocket up. So how does that work? For a rocket to fly, you not only need to have enough fuel to bring it to the atmosphere, you need that fuel to give you enough energy, enough velocity to impulse your rocket up and to burn for long enough for you to overcome gravity. Because as you studied in your courses in AstroCamp, getting to the escape velocity, it's actually harder than it seems. So you would rather have a constant velocity that doesn't involve you get the escape velocity from the ground. So how can you do that? First, your fuel and oxidizer, basically you just need something to burn in. but they are usually gases, and gases occupy a lot of space and are not very efficient. So what you start by doing is by compressing those gases into the liquid form and putting them in containers that will expel them at high pressures. So by the moment they get together, you just need a little spark for a very big acceleration, because both the pressure and the nature of the propellants will make sure that you have a big enough explosion to put your rocket in the air. Usually, rocket fuel is not an exact science per se. You can use different fuels for different goals. You can want a longer burn, you can want a stronger burn. It all depends on what's your goal and how you want to do it. But one of the simplest examples is thinking, we are talking about an oxidizer. So what's the most natural thing to have to oxidize a fuel? Oxygen. Just need something where it can burn. And what can burn with oxygen? Hydrogen. Everything, things that are in our atmosphere and in big enough quantities for us to use. So it's not that hard to think about the fuel you need. You just need to know how to use it properly. So that's the basic physics of a rocket. You need to throw something hard enough and fast enough to make sure that your rocket goes up. So let's say that you've studied this, you know how this works, you know how much thrust, how much force will your rocket engine give you. How can you create a rocket around this engine? How can you make sure that giving these initial conditions, you can get the payload you need in the atmosphere? So you start very simply. You start by drawing a body. So the first thing you must consider when studying a rocket is what kind of structure you want from it. When thinking about the structure, there's three very important things you need. You want to avoid air drag. You don't want the air resistance to be too high. So air resistance can depend on either V squared or V. That depends on the form of your rocket. So if you have a flat surface, you'll have a dependence on V squared. If you have a cone, you'll have a dependence on V, so the rocket will cut through the air molecules and fly faster. Of course, you want a dependence on velocity alone, not velocity squared, because the bigger the drag, the harder it is to put something on air. So you build something that is very aerodynamic. Secondly, you need to think about two things: the center of gravity. Basically, if you consider every single point of mass of the rocket and you average it, and you can get a point where you consider all the forces that act on the rocket to be acting there. Why is this important? Because the rocket will tilt over the center of mass. This will be the rotation point. So if you want to avoid your rocket to go like this, or this, or this, or this, or around itself, you need to know exactly where it will start rotating. Secondly, we have the center of pressure. So let's say your rocket is in the air. You'll be having a drag force and a lift force. So your rocket fuel, when you're expelling it, it's causing the force. And you'll be feeling the air resistance on the top. There will be a point in your rocket when it's going up that both forces will cancel out at that point. This only exists when the rocket is in the air. But it's very important when you're thinking about how stable you want your rocket to be, because if you have a rocket that is not stable, it will wobble, 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 and it will never reach high altitudes. So what you need to consider is that your center of pressure must be always behind your center of gravity. Why? Let's think about it. The forces cancel out here, meaning that the drag force will be higher than when you go up the center of pressure. That will cause a higher wobble and affect the stability. So how do you want your rocket to rotate? You don't want it to rotate at all. But if it has to, you can better correct things where it's closer to your thrust than when it's on the nose of the rocket and there's nothing that you can use to make sure that it keeps going straight. So you must have your center of gravity on top of the center of pressure. How can you measure this? Of course, there's optimal distances. You don't want to have a center of gravity here and the center of pressure here, because too far away also can cause rotation. what you want is to find a measurement in terms of the rocket that allows you to find the best position to put them. That's what we call calibers. So we take the diameter of the rocket, and we know that those two centers must be between 1.5 and 2.5 calibers in one. Of course, that's not the only things you need to consider when evaluating the stability of a rocket. You also need to think about mass distribution, what can cause a torque. So if you have too much mass on the left, too much mass on the right, how that can affect how your rocket will behave. You need to consider the shape of your rocket. Again, air resistance can tilt it to one side or the other. So you want ideally a rocket that is symmetric and equal in all sides. You need to consider the length of the rocket and how that will cause any more torque and cause it to rotate. And that's all things you need to consider before put your rocket in the air. Fortunately, there's loads of simulation programs you can use and search online for that tell you more or less how your shape, how your design will behave in real life. Second part, electronics. So let's say we have a rocket engine. You have a rocket. You've built your rocket in terms of the engine, so it will more or less fit you what you need. Now you need it to work. What you need to consider, the brains of the rocket, the electronics that will give it life. So what is this about? This is about the flight computer and every single thing that it will control around it. So let's say you have a rocket and you need to keep track of it. You need a GPS. Let's say you want to see how it is behaving during flight. You need a camera. Let's say you want to see how high it is. You need a barometer, because your GPS usually is not very well reliable at high speeds and high altitude to tell you the altitude, so you need something else. And then let's say you'll need to find your speed and acceleration while in flight. How do you do this? You get something that is called an inertial mass unit. Basically, it's a gyroscope and an accelerometer in one that tells you both the positions X, Y, Z, and allows you to find the acceleration of a rocket and the velocity of a rocket in the three components of movement at any time. Then you need to think about, how can I get this thing back on Earth? Do I need something special, like some electronics system that will make my parachute shoot? Do I want any active flight controls, like an air brake, or like a reaction wheel that will stop the rocket from turning around itself? Or do you want to have some servos that will rotate the engine so we can use thrust vector controlling? And at last, how can I save my data? How can I receive my data? How can I learn from this flight? That's the telemetry. You want two things. First, when you're flying very high and very fast, it's very hard to transmit information in real time. So you want to have a black box. You want to be able to store your data safely in a way that you can retrieve your rocket and learn from your flight. And then you want to be able to transmit something. I mean, you've launched your rocket, you want to catch it, but you don't have a GPS. That can be a radius of kilometers until you find anything. So ideally, you have your rocket transmit you GPS information so you can find it. And then the last thing you need to think about is your power sources. So let's say you have a flight computer and some servos. How are you going to power that? How much energy you are going to need? How will this affect your mass distribution? These are all things you need to consider. So basically, in electronics, you have your flight computer and everything else that will need to be attached to it. In terms of flight computer, there's two very different approaches you can take. You can choose to have a somewhat more powerful computer ready off the shelf. For example, Raspberry Pi, that you can just attach some of the GPS, the IMU to it, and use it to fly. Or you can design your PCB or your own circuit boards. The advantage of designing your PCB is that you can save on power and you can save on weight, which are two very important things when you're designing a small rocket. You can choose a smaller computer that has a lower capacity, but good enough for your flight, and that doesn't require as much energy. You can choose the best IMU you can get the best GPS. You can design things for what you need instead of putting things into your rocket that you won't need, but because they are on the computer you're using, you're wasting space and energy on them. And this is a kind of trade-off you need to consider when you're starting to design your rocket. Then, I've already touched on this, but you need to think, after you design your rocket, you have the brains of the rocket. But before putting your rocket in the air, you need to think, how the hell am I going to get this back on Earth? How can I get my rocket safely to me, to recover my data, to study again, or even to launch it again? So you need to think about the recovery. Traditionally, especially on model rockets, you just use a parachute. And there's a very simple equation that equates the weight of your rocket, the density of the air, the flow speed, and the drag coefficient, all quantities you can measure, to the area you need to have in a parachute in order for your rocket to go up. Furthermore, when we are talking about parachutes, then you need to think, okay, I know the area, I know the material I need, how can I get the parachute to launch when I'm falling? So probably you'll want to have a kind of an hydraulic system, a pressure system that will make sure that when the time comes, your cone will open and will launch the parachute up. Another non-conventional way, and one of the things I'm working with Endeavor, is thrust vectoring control. So basically, what you have is that when you have a rocket, you're sending thrust downwards. Your rocket will invariably start wobbling. It's a chaotic system. There's nothing you can do to avoid some kind of wobbling. What you can do is make sure that it keeps in place. So the basics of thrust vectoring control is my rocket starts tilting this way. So I tilt my engine and make sure that the force that it's putting will rotate it that way. So whenever it goes like that, I send it back flat and done, and it starts oscillating along the equilibrium position that makes sure it keeps a stable flight and that it can land on itself, because this works for when it's going up, but it also works when the rocket is going down. And at last, in terms of an anatomy of a rocket, the last thing you need to consider is you have the brains, you have the body, you know how it will be going in the air, and you know how to recover it. You need to think, what kind of logic must my rocket follow in order to do what I want? That's what you do with your software you're going to put in your flight computer. So, some things to consider. Most of these flights are very, very short. A few minutes, sometimes a few seconds. So you won't have time to send real life commands. You need the rocket to do the different activities you want it to do by itself. So you need to consider, how can I structure my code in such a way that my rocket will respond to all the situations it will encounter? That's where the logic of a software comes into. You need to consider, what will the rocket do before flying? Is everything working properly? Is anything wrong? So you want a pre-flight stage where the rocket will go through every system it has, make sure everything is working fine, and, for example, light the green light if it's ready to take off. And then you want to make sure your rocket knows where left and right is, up and down, because most of these systems you put, the GPS, the National Mass Unit, they tell you your position in the grid. But to set up the zero and to tell you where is your 0 point, that's not straightforward. You need to program that into your flight computer so it knows where to start from 0. So that's what you want. Let's say I have my rocket on the landing platform and I want it on the launching platform, and I tell him, okay, this here is your point 0, 0, 0. When you go up, that's your z-axis. You go this way, it's your x-axis. You go this way, that's your y-axis. You need to tell your rocket to do that. Second, you want it to get ready for liftoff. So maybe send a radio sign, tell your rocket to fire up the engine and start going up. During the liftoff, you need to make sure that your rocket is prepared for high accelerations and high velocities, because it's going to go very fast. After liftoff, after and during liftoff, you need to make sure that it doesn't wobble, because the smallest wobbling during this stage, since it's a high acceleration, means that your rocket can go very wrong very fast. So if you have any active control measures, that's the time to use them and to make sure they are working properly. So that's what the kind of calculations you want your computer to be doing during the liftoff, making sure the rocket is going straight, making sure it's not rotating around itself, and trying to identify when changing for the next stage. Because once you're in flight, you're on the ground, you're no longer in control. You need your computer to be able to do it by itself. So how do you do that? You tell your computer to start reading your acceleration, your velocity. So until your fuel burns completely, your acceleration and velocity will be increasing, right? The moment your acceleration and the velocity start decreasing, that's when you enter your demand flight, meaning you've burned everything and you need to start to prepare for the next stage. So what you need to think is what kind of conditions you need your rocket, your computer, to identify, to switch off to the next phase. So let's say you enter main flight. That's when you can perform experiments, maybe start sending GPS data, because at high velocities it's very hard to get accurate data. But when you start slowing down, maybe you can send the data with the highest altitude straight away from there, so you know, and you want to start thinking about when to start the recovery phase. So once you fulfill the main flight criteria, your program will change directives and start taking measurements, sending measurements, maybe send a live feed of the camera of your rocket, and start making the measurements and the calculations you need to know to identify when you've reached your peak altitude. Because once you reach your peak altitude, you need to start thinking about recovery. So let's say your rocket stopped burning and is deaccelerating, but the velocity is still increasing and the altitude is still increasing. So you're still going higher and higher and higher. So you can tell by your data of altitude, when your altitude is no longer increasing and starts decreasing, that you entered recovery mode. And that's what you want your computer to identify. So let's say you have a barometer that can, through some calculations, some coding, tell you how high you are. Once you get your data from your barometer saying, I'm no longer in my highest point, your flight computer will change again and go into recovery mode. Then it will identify your high and identify the exact moment it should release the parachutes to recover the rockets intact, and hopefully start sending a GPS signal so you have an easier time finding your rocket, because that can be one of the main problems. So this is more or less the logic you should follow in any rocket flight. Think about the stage and make sure that your code, that your computer is autonomous enough to be able to perform all these tasks without you, and to be able to deal with any problems that may arise from this. And this is just an example from my team. This just shows you a slightly bigger rocket for a competition. Way more stages, way more complex. But the basic stuff, the basic criteria, the basic things you need to consider are in the previous slide. Then you have your rocket, you know how to fly it, you've built it. What can you take from this experience? Why is amateur rocketry so important? First, you can do cool scientific experiments. Let's say you have a rocket that goes until 1 kilometer in the atmosphere. You know, at that altitude, you can count the number of muons in the atmosphere, compare that with the altitude data, and test the principles of special relativity, which you've talked about during this week. This example is from Endeavour muon experience. Then other things, like, that's not only related to physics. Let's say you have a biology experiment. You want to test how cells will grow or develop, or how high accelerations and high variations of acceleration and velocity will affect the cellular structure of animal and vegetal cells. That can be done by having a small petri dish in your rocket, and when you recover it, you can study and analyze that through the microscope and see how everything goes. You also learn loads of new skills. You can learn new coding language. For example, what I was talking about, the simpler the computer, the less the energy you need, and the more efficient your rocket will be. That has advantages, but it also has disadvantages. For example, you can choose to use an Arduino Nano or a TNC Studio. In my case, I use a TNC Studio. Those kind of computers only work with C++ language. So you'll have to learn that because it's a more efficient language that allows you to store more information in less space of memory. So that's the most efficient way to do this with small rockets, where every single bit of space is accounted for. Then you can try even weirder stuff. Let's say you reach uni and, okay, I know the basics of rocket technology, but I think I can do a better engine. I bet I could create something more efficient. You can go study the models. You can go try to build your own design to see if it works. Of course, it's not as simple as it, because most rocket engines are considered bombs. So you need to have some authorizations and to do some partnerships, but it's doable and you can learn things from that, both in chemistry and physics. And at last, you can explore mathematical concepts. Throughout this presentation, I've talked about the thrust vector control. Let's think about it. You're giving small pushes to one side or the other, but how do you know exactly what's the angle and how much force you need to do? How do you avoid, like, if my rocket is here, sending like that? That's control theory. That's a mathematical, one of the branches of maths used for engineering. And you can test that with your rocket, and you can see slight variations in your, use slight variations in your code to see what's the best way to do it. Actually, that's what I'm doing in Endeavor. Basically, take a very powerful fan, an EDF, I usually call it an oversized air dryer, but basically something that impulses your rocket up, and you test your code multiple times, and you see which kind of slight adjustments you can do to make sure your rocket stays straight the best you can. And at last, you can go to competitions. This is all based on my rocket team. This is the launch on Europe. We launched in 2022 on actually Algarve, because Europe happens in Portugal every year. And even if your rocket doesn't survive, you can still win prizes. Our rocket, we had a problem with the pressure chamber where we had to put a hole on it. So the pressure chamber will make sure that the parachute will come off and the nose will jump. There was a hole on it. So as you can guess, pressure chamber hole doesn't work quite well. So our parachute never came off. So our almost 2 meters rocket came down to more or less this size. However, we did the new one experiment, and people like it so much that they gave us the payload award. Payload is the thing you put inside your rocket to perform experiments or potentially send it to space. Or let's say you build your own rocket engine, you can go to the UK race to space, where we didn't win anything. We went there this year, but we had the chance to show our designs to experts in the area, industry experts, and they gave loads of advices for the next project, for the next design, and how we can improve. So that's all the cool stuff you can do with rocket building and with this knowledge. So how to get started? I said I would have some links. So the best place to get started, I would say, is with other amateur rocketry websites, YouTube pages. In this case, it's BPF Space. This is a guy who decided, I want to work for NASA, but I have no knowledge. So let me try to build my own rocket first and show them I can have what I did in my CV to work for them. And he posted everything. He actually managed to construct a successful thrust vectoring control rocket. And he posted that and all the updates online for us to follow into and to explain us how to do it. Then you have to learn C++. That's one of the things you'll probably need for your rockets. You can use a C++ tutorial. That should be. This is one very good one, and that's why I put there. And at last, no one expects you to start from scratch. You need parts, pieces, engines, fuel. You can get all that on the Rocket World, European Union authorized seller for rockets. And that's all my advice. So hopefully you get a better idea of how to build rockets. I know some of you already have some experience, so I taught you something new. And any questions, just shoot it.